All right, so Kepler's law of periods says that two objects orbiting the same central point have the same Kepler constant. So this question is about Pluto, and the other object that I know information about that orbits the sun is Earth. All right, so I'm going to take the period of Earth squared divided by the radius of Earth's orbit cubed and say that that is equal to the period of Pluto's orbit squared divided by the radius of Pluto's orbit cubed. Okay. This question wants me to calculate the mean orbital radius or average orbital radius of Pluto. And average is important here because, as we looked at yesterday, Pluto's orbit is highly elliptical. Right? It's not a perfect circle. All right, so I'm trying to find the radius of Pluto's orbit. That's here. So I'm going to bring that up over here and then manipulate everything else. I don't want to solve for it on the bottom. Okay, I don't want to find 1 over the radius. I want to find the radius itself. So I'm going to multiply both sides by the radius of Pluto's orbit cubed. Okay, and then I'm going to multiply both sides by the radius of Earth's orbit cubed. And then I'm going to divide both sides by the period of Earth's orbit squared. Okay, so what I'm going to be left with is this. The radius of Pluto's orbit will equal the cube root of all of this, because that was cubed. Okay, so the period of Pluto's orbit squared times the radius of Earth's orbit cubed divided by the period of Earth's orbit squared. Okay, so now I've got to punch in those numbers. I can use whatever units I want as long as I have the corresponding units given to me. Okay, they gave me days. So I have to use the Earth's orbital period in days. Okay. All right. So that means then that the radius of Pluto's orbit will be the cube root of 90,553 squared times the radius of Earth's orbit. Did they tell me what units I had to find? Good. Then I'm going to use astronomical units. 1. Okay. Astronomical unit, remember, is the distance from the center of the Earth to the center of the sun. 1. Okay. And then I'm going to divide that by the period of Earth's orbit, which is 365.25. Remember, that's why we have a leap year every 4 years. There's an extra quarter day that we have to account for. All right. So when I plug that in, I am going to have, okay, so you have to hit the math button and then 4 to get the cube root. Okay, and that's going to be 90,553 squared divided by 365.25 cube, or squared, sorry. All right, so I'm getting that Pluto is 39.5 astronomical units from the sun. So almost 40 times further from the sun than Earth. Okay, it's a long, long way. All right. Okay, I'll give you guys a little bit of time on question number 3, which is talking about the rocky debris somewhere out in the Oort cloud, I would imagine, with an orbital period of 302 years. Okay. All right, so for number 3 here, okay, we have the mean orbital distance or orbital radius for this piece of rocky debris, and I'm going to set it equal once again to Earth. So the period of Earth squared over the radius of Earth's orbit cubed equals the period of the rocky debris's orbit squared, okay, divided by the radius of the rocky debris's orbit cubed. Okay, and we are looking for orbital period, so we simply multiply both sides by the radius of the rocky debris's orbit cubed. Okay, and then we square root that. All right, so what we will have here is the period of the rocky debris will equal the square root of 45 cubed times 1 squared divided by 1 cubed. So really we're just looking for the square root of 45 cubed. Okay, that's the beauty of using Kepler's law of periods, small numbers. Okay, when I teach you about satellite motion, okay, you're going to see that the numbers we use for that are always very, very large. However, using satellite motion to solve orbital mechanics problems always works. This only works if I have information about 2 things orbiting the same central point, and that's rare. Okay, it's pretty rare. So if I use, let's say, a question like this, but I gave you the moon, okay, could you use Kepler? No. Do you know the orbital period of anything else orbiting the Earth? I don't either. Okay, so I can't use Kepler in that case. I don't have information about a second object orbiting the Earth, so I wouldn't be able to find out what the moon's orbital period would be. Okay.
Sometimes you gave us the orbital period, but you asked us to find something about a satellite orbiting.
You could, but it's almost, that one's almost easier to solve as a satellite problem. Okay, so when we plug all this in, really we're just looking, like we said, for the square root of 45 cubed. So square root of 45 cubed. All right, 302 years. Long time. Wouldn't get your first birthday, ever. Okay, questions on Kepler's law of periods? Everybody good with that? Okay, like I say, it's not something we're going to use often, but if you run into a situation where you can use it, it's nice because it's small numbers, pretty easy formula to manipulate. All right, the other day we did not get a lot of time to practice using Newton's universal law of gravitation, and I want to make sure we're good at that before I go into satellite motion, because you have to use that formula a lot in satellite motion problems. Okay, so plan for today is that we're going to spend some time working on those gravitation problems, and that's not it. No, that's not what I want. All right, be that way. All right, so I'm going to want you guys working on these problems here. We didn't get to, I don't think we even got to working on these, did we? Okay, so let's just start on question number 1 here. Okay, they're just FG equals big G times M1 times M2 over R squared kind of problems. They shouldn't be too tough. Okay, I don't think we'll spend the rest of class on this. I'll start talking about satellite motion here before the end, but got to make sure we know how to do these. Okay. So yesterday we were talking about Kepler and how he came up with all these ideas about how the planets move around the sun. And the big thing to remember about the brilliance of what he came up with is that he had no idea about gravity. Okay, he figured out that planets orbited the sun without an understanding of the force of gravity. Okay, the thing that makes that happen, and he figured out that they do it without knowing how. Okay, that's, when you think about it, that's pretty amazing. That's why, I mean, everyone thought the Earth was the center of the universe. No one had any idea that the Earth was so small, okay, and that the sun was, you know, hundreds of millions of times bigger. Okay, they just, no, that's what we see in the sky. Okay, this guy figured this stuff out without an understanding of that the Earth is so much smaller. Okay, so what we got to look at is, why do satellites do what they do? Well, satellites do what they do because of gravity. Okay, the centripetal force that keeps something orbiting something else is provided by the force of gravity. Now, when we use force of gravity here, it cannot be m times g, because g changes depending on how far from the Earth we are. And we don't know what it is at all the different altitudes. So, okay, we have to use Newton's universal law of gravitation instead. And so what we end up with is this: mv squared over r equals big G times mass 1 times mass 2 over r squared. And we actually did a problem like this when we were figuring out how fast the moon was moving in its orbit around the Earth. Okay, and we solved for it. It was like a kilometer per second. Okay, things we need to remember about this relationship. Okay, it looks like there's 3 m's in this equation, but there's actually only 2. Which one's on both sides? The satellite or the object being orbited? The satellite is on both sides. The satellite we'll say is mass 2. Okay, that means it's the one that's moving in a circle. The one being orbited isn't moving it. Well, it kind of is, but we're going to say it's not. Okay, that it's not moving in the circle, but the other object is. All right, so mass 2, or the mass of the orbiting object, ends up on both sides, and as a result, anytime I do a manipulation, that mass is going to cancel. Okay, and the reason for that is because even though we're not using this formula, sorry, mv squared over r equals m times g, it's still true. Agreed? Okay. And that means that all things fall at the same rate regardless of their mass, because g is acting as a centripetal acceleration. And it would be the same for any object regardless of its mass. All things fall at the same rate. Okay, everyone all right with that idea? Okay, so that's one of the things we have to remember, is that the mass of the satellite is essentially going to be irrelevant. Okay? But this radius is something we have to be mindful of. Where is that measured to? Right, the center of both objects. It is the distance from the center of the satellite to the center of the orbited body. It is crucial that we remember that, because the most common trick that can be played on you in a satellite motion question is to give you the altitude of the satellite. Where is that measured from? From the surface. Okay, so a question might say it's orbiting at this altitude, or it might say calculate the satellite's altitude, in which case you would have to remember you're either adding or subtracting the radius of the orbited body. Okay, one or the other, depending on whether you're given it or asked for it. Okay, you'd either add or subtract. So it's one of those small tricks, because mathematically these are not really difficult questions. Okay, the trick comes again in the context of the question. All right, so we need to understand that satellites obey uniform circular motion laws. Even though they move in ellipses, they're still essentially circles. Okay, understand that for all orbiting bodies, gravitational attraction between the two bodies, that's this formula here, okay, provides the centripetal force, and that orbit is achieved by making sure a body travels far enough that the distance the satellite falls is equal to the distance that the object it's orbiting curves away, because obviously it's orbiting something round, not flat. Crazy, crazy people. Okay? The Earth is round. I think we've said that a few times. We've established that that is fact, and that flat Earth is crazy. Okay. All right. I can't believe that flat Earth thing is still out there. Come on, Columbus. That's like 1492. Okay? We've been pretty sure of this for like 500 years. Okay. Sorry, my rant is over. It's over now. Okay. So here's the thing about Newton. He was way ahead of his time. I mean, there's no doubt about that. The guy was way ahead of his time. So far ahead that he wanted to run experiments that were impossible, given the technology available to him. So he started running thought experiments, which means he would think crap up and then tell people how it worked. And they would go, well, you're Newton. You're probably right. Okay. Okay. Because they couldn't actually perform the experiments. But he said, hey, I'll bet you this would work. I'll run it in my head, and that'll be cool. And then I'll write it down, and you'll all buy it. Okay. And they did. And he was right most of the time. Okay. Thought experiments just worked well for him. And you can't get away with that now. Okay. You can't run a thought experiment now. Now we call that theoretical science. We don't call it a thought experiment anymore. Okay. Okay, so here's Newton's idea. His thought experiment was this. I take a cannon to the top of a very tall mountain, and if I can shoot the cannonball fast enough, it'll orbit the Earth. True. 100% true. Essentially, that's all a satellite is a projectile. A projectile that moves so fast that the distance it falls is equal to the distance the Earth curves away while it's flying. The problem with the experiment is that near the Earth's surface, this object must travel 8 kilometers per second. Per second, okay? Because it's going to fall 4.9 meters in that first second. So it's got to go far enough that the curvature of the Earth will equal 4.9 meters. That's 8 kilometers given the radius and curvature of the Earth, okay? We cannot make anything go 8 kilometers per second within the Earth's atmosphere. It would vaporize. Okay, that's why things burn up when they re-enter the Earth's atmosphere. They're going really fast and there's a lot of friction. Okay, we can't do this. It's a nice thought experiment, but we can't do it. But we can do it if it's not near the Earth's surface and outside the Earth's atmosphere. Then this works perfectly.
Also fail though, because wouldn't you get slowed down by like air resistance if it didn't?
Oh, absolutely. I mean, there's all kinds of problems with this thought experiment. It's a nice thought experiment. It's not a good practical experiment. Okay, you fire this cannon, and the cannonball is going to go, and that's it. The end of experiment, right? Well, I mean, it doesn't even have to be any wind. It just has to travel through the air. The air will slow it down, right? So this obviously in practical sense wouldn't work, but in a theoretical sense, it works great. Okay, and it's how we get satellites in orbit. And even in orbit outside the Earth's atmosphere, they still have to move pretty fast. Okay, we already found that even the moon at the distance it has to move at 1 kilometer per second. 1 kilometer, not 8. Okay, but 1 kilometer per second. So things in low Earth orbit still have to move pretty fast. Okay, several thousand meters per second for sure. Okay, everyone kind of follow me there? All right. So that was Newton's thought experiment. Okay, he drew pictures like this one. Somebody standing on top of a big pedestal could throw a ball or throw an apple because it was Newton. Okay, and if they could throw it hard enough, then it would orbit the Earth. If they didn't throw it hard enough, then it was a projectile, and would hit the Earth. Okay, but if you could throw it fast enough, that projectile arc would continue. But if this is a cannonball, fire that cannon and then get the heck out the way. Because if it works, that cannonball's coming back. Okay? It's going to come all the way back around and get you in the back. Okay? You don't want that. Right? Now, obviously, we said it's not going to work. It could, I mean, unless you were standing at the highest point on Earth, it wouldn't work. And even then, we've already discovered that the Earth's not perfectly round. If I fire something from the top of Mount Everest, it could still hit the equator at sea level because that's apparently further from the center of the Earth than the top of Mount Everest was, right? Because the Earth's not perfectly round. Not perfectly round, still round. Still round. Okay? It would depend on a lot of things, radius, speed, all that kind of stuff, yeah. All right, so everyone's okay with that idea? Okay, so that's the basic mechanics of orbit, okay, of satellite motion. It looks really simple, and in fact, it is. The complex part of it is making something go fast enough, high enough to do this. Okay, who were the first people to do that? The Russians, yes. The first satellite was Sputnik. Okay, Sputnik was the first thing to ever orbit the Earth, and it scared the ever-loving you-know-what out of people. Okay, especially the Americans. Okay, because the Russians put something like a basketball with antennas on it in orbit. Okay, and all it did was orbit the Earth and beep. Okay, that's it. That's what it did. It orbited the Earth and beeped, and they made sure they gave the Americans the frequency so they could hear the beep. Okay, because what did it say to the Americans? Hey, we can put something in orbit. That something could be a bomb, and we can drop it on your head. Think about that. And that's exactly the message they were sending when they did that is, hey, look what we can do. Now we can put anything anywhere on Earth we want because we can put it in orbit and then make it fall. Okay, it was a pretty scary thing for the people of that time. Okay, it was a basketball that beeped and went around the Earth, but it was scary, okay, for that reason. All right, and then of course the race was on, right? Who could get a man in orbit first and all of that, and of course the Russians did that first too. Yuri Gagarin was the first person in space. And then the programs kind of took off from there. There was the Mercury program, which was just about kind of low Earth orbit stuff. And then there was the Apollo program after that, that was getting people to the moon and so on and so on. Okay. All right, so motions of planets and satellites. So a satellite in orbit is always the same height above the Earth. Okay, it's always falling, but never getting closer to the Earth. Okay, its centripetal acceleration is, like we said here, AC equals V squared over R. That A would be whatever little g is at that point, okay, or at this radius. So that would determine how fast it needs to go. Okay, so essentially what we end up with is the formula we just talked about. Big G times the mass of the orbited body, okay, times the mass of the orbiting body over R squared equals mv squared over R. Okay, obviously the mass of the satellite cancels in that case. Okay, questions on that? Okay, there are different kinds of orbits. We'll look at that kind of stuff on Monday. Okay, we also need to look at when we don't have V and how we substitute this formula in to here. Okay, I've shown you that once before, I think, but I'll show it to you again. It's important to be able to make that substitution into that formula, and that's what we'll talk about on Monday.